host today is Andrew Brown from University of Liverpool. He is going to talk about Eremenko's conjecture, Devaney sayers, and the growth of counterexamples.
Very well read. Okay, so after several days of masochistic amounts of maths, I'm going to be moving around enough to hopefully you can just at least track me. And you'll be glad to know there's a lot of pictures. There's not so much details to go through. I mean, professionals, feel free to fall asleep. Amateurs, you might see something you've not seen before. Anyway, let's move on. So start with some basics. We're going to be looking at transcendental entire functions, basically not a polynomial. Going from C to C, we have two set, nice and stable, Julia set, chaotic. And then for transcendental, the escaping set, that last one is the one of interest for transcendental. The other two we know for polynomials, all right, but this one is interesting. Okay. Now, for a transcendental entire function where we have issues inverting, we'll try and work away from them. And so what we look at are either the critical values, just the same place with the derivative zero, invertible function theorem, all that. But for transcendentals, we also have asymptotic values, i.e. these are values that we only attain when you go along some curve to infinity, and it's a value there. So an actual example, the exponential go down the negative real axis, exponential of minus t goes to zero, but we never actually hit zero with the exponential. Okay, now this set of troublesome values we put together, we call the set of singular values. So you have your asymptotic values and critical values. Take the closure, well, there it is. But now we've got a new set to look at and to think about. So let's classify, let's look at how, we've got a new set that's a subset of the complex plane. We know a lot of things about subsets of the complex plane. Okay, and so in words, if you have a point alpha in this singular set, there's some troublesome inverse image. So you may get bijective inverse images, but there's going to be at least one component that doesn't work. Okay, oh, there we go. Okay, and as I just said, if we look at our singular set, you can either have ones that are in the Spicer class or the Eremenko class. Other classes exist, but these two are ones that we're interested in. And obviously that's S for Spicer, but I'll move on to B in a second. So the Spicer class, it's when this set is finite. We have, you can list them all on your hands or count them even. Now, an example, cosine, -1 and 1. Simple enough. Okay, there we go. Now, the B for Eremenko-Lubitsch is actually for bounded rather than E or L. And an example of this, sine of Z over Z, this does have infinitely many singular values, however, they're bounded. A quick calculation shows that the modulus is, like, you basically have to solve Z equals tan Z, and you get real solutions, and the moduli are less than the modulus of cosine. So we're bounded by 1. And as stated, that shows that the two classes are distinct in a way, like they're not identical. Okay, and for us, we're going to be looking at class B. So Spice class is contained in class B. Let's look at the bigger one. Now, we've just said that those singular values are bounded. And let's see if this is slightly less sensitive. There we go. So we're moving on to pictures, as I said. Now, given the restrictions of hybrids moving between different cameras, this is all unashamedly done in very crude paint drawings, because anyone who's been writing on a tablet, their pictures are going to be of the same quality. So I've just skipped the middleman. Okay, so first of all, we're going to consider the set of singular values for one of these class B functions. And we're going to add in 0 and f of 0 as well. Just entertain me for a second. Okay, here are the crude images. So there we go. We've got 0 and f of 0 in blue and all of our other singular values. They may be infinite, but we can bound them. There's some disk that sits around. Let's look at the red part outside. Okay. Since we're working in that red part and we've avoided all of the singular values, we can invert. So we call that complement W. Let's take its inverse image. And we get this collection of things. We call these tracts. Okay, and these are simply connected Jordan domains. And, well, why did I include 0 and f of 0? Well, so you can take a logarithm. Because then when you take a logarithm, we end up with nice periodicity because of the exponential. Okay, so if I go back to this picture for a second, we just take V out of that collection of tracts. Just pick one of them on the left-hand side. And we're going to take the logarithm of that one single component. Okay, so we take the inverse image upstairs and you get the 2 pi I periodicity going up. Okay, and then on the right-hand side, we're outside of 0 as well. We can take a logarithm of that. Logarithm of the complement of a disk is going to be a half plane going to the right. And whenever we have 4 pictures that we provocatively put into a square, we like to fill all the edges. Can we fill that top edge? And we can. We always like a commutative diagram. Okay, so I'm talking ahead in my slides. Yes, we can. So we do that, and here's an actual good image from Dave Sixsmith, and the upstairs function we call capital F. And this capital F is the one that we're going to be working with mainly, because in a second, so yeah, we call that logarithmic transform, and what we like to do normally, if I go back, those tracts T on the left, if you superimpose them on the copy of the complex plane in the top right where H is, we like it so that the tracts are in the half plane, that they sit to the right, because then when you take forward images, you stay in that half plane, so you don't end up leaving by mistake. And those ones are called disjoint type. Okay. So I've given you a graphic description, but that's in symbols roughly what we like. Okay. We have expansion properties from it's Eremenko Lubitsch 1992, I think. There's an expansion property, but we're assuming that we carry on staying in the right half plane, because I could really make this a long talk if I wanted, but anyway, so if I go back to this picture for a second, as I just mentioned, we'd rather work upstairs, but the way we've constructed this is by starting with little f down, and then we've given ourselves big F upstairs. We can work upstairs quite easily. We can construct artificial versions of those tracts, but just because we do that, does that necessarily mean we can move back downstairs and have a corresponding little f? And we can, by some approximation theory in the paper by Rottenfusser, Ruckert, Remper, and Schleicher, of which we have a Schleicher here and a Remper hopefully online. And so without going into details or justifying, yes, we can construct upstairs and find a function downstairs in that square. Okay, and in doing that, we just use some of Carathéodory's theorem, Riemann maps. But basically, we can fill in that square. Now, to actually talk about the title, because I've not mentioned any of those items yet, we have for 2, yes, it was for 2, the Julia set of the sine family up there, they have curves of points where all the points go to infinity, and it was sort of, this is interesting, this is a nice property. And Eremenko then studied this further in 1989, I think, where he was asking, can we do this for more general functions? And he has shown that if you take the closure of the escaping set, then it's unbounded. Every component is unbounded for an arbitrary class or for an arbitrary transcendental entire function. But then what about just the escaping set itself? Okay. Now, the weak form of the conjecture is that for an arbitrary transcendental, does the escaping set comprise of unbounded components? But for a stronger version, we have this form where we say for every point in the escaping set, it can be joined to infinity by a curve within the escaping set. Okay? And these are called Devaney hairs. So that's 2 out of 3 of the title. Back. Okay, and in that paper I just mentioned, this was shown to not be true by counterexample. And this was for even class B functions. Not all of them, but examples that are in there. Okay. Now, it's not all bad news. Eremenko wasn't completely off. There was a boundary that we can put down. And if you have a function of finite order, that is this, for anyone who was in my position when I first started learning this, I didn't know anything about Big O and Little O. So that's there for anyone who doesn't know. And basically, if you do have a function class BF that is of finite order, Eremenko's strong conjecture does hold. You do get these Devaney hairs. Okay. Now, how is this counterexample constructed? Well, as mentioned, the construction was done in the upstairs part where we have the logarithmic transform. Using the approximation theory, we can then say, yes, there does exist a class B function of finite order, or not of finite order, that does this. Okay, and the way that this is done is by constructing this sort of a tract. It's just a rectangular one, even though the picture had wiggly ones, just a rectangular tract with these wiggles involved. And then there's without going into the details of the recurrence relation, there's basically a sequence of geodesics used. And then there's a counterexample, or a contradiction rather, by assuming there is a curve. And thankfully, you just need to follow the pictures, really. Ooh, there we go. Okay, so as mentioned, this is the tract. The blue dot in a lot of the constructions that I've been working on and looking at, that's about 5, just on the real line. So the real axis cuts through. And the dots there, they just sort of indicate, imagine that this continues for another, I don't know, n-2 or n steps. Except this doesn't really justify it. The gaps are exceedingly large at each step. So it rarely stretches out between the wiggles. If I'm not too sensitive, there we go. So because this is in a half plane that's going to the right, the geodesics are half semicircles centered at the origin. And so if you go far enough across, these arcs cross across the tract. And because it's disjoint type, this tract is in that half plane still. And then if you take pre-images of these two geodesics on the right, they go to those red geodesics on the left. And the reasons for why they are of this shape, it's justified in the paper, but just follow the pictures. It's the end of the day. I'm going to do this because the mouse is too sensitive. I'm talking to it. Okay. So this k for the arcade, that's just some k greater than 0. It's a natural number. Now, if we were to have a curve going to infinity, it's had to go through all of these wiggles all the way past through here. Okay. So imagine that we did have this curve all the way up to here. If that was to happen, then
sorry, Andrew. I think in your picture, the second set of green lines has moved a bit too far to the right, because it should be sitting within the, like the previous one, it should be sitting between the two ends of that wiggle, shouldn't it?
Yes.
Because those two green lines are actually very, very far apart.
Mhm.
So they're not going to be right inside one of those little bits where the track turns around, but they'll be kind of inside the wiggle, which might be confusing. So I thought I'd point it out. Sorry.
Oh dear. Well,
No worries, but I just thought in case it confused. I think it's just a technical thing that they've been moved to the right, but people might otherwise get confused.
thank you, Massa. Well, as you've all just heard, my picture's slightly wrong. The crude version of this does have the correct ones in, apparently. But the crux of the contradiction is still contained in this, hopefully. So anyway, we've assumed that we can get this far at least. So between RK and RK, with hopefully you can see there's a dot on top. Let's look at that blue section. Because we're talking about a Riemann map that goes from this tract to the half plane, it's not isomorphism of some sort, i.e. that blue line gets mapped back to the geodesics that were the pre-image. Now, looking at this part here, there's now two sections of this geodesic that got mapped back here. So now if we were to then take that back another step, we'd end up with 4. Back again, 8, etc., etc. So eventually, by mapping backwards, assuming we can do it up at k, we should then have 2 to the k of them at the very start. And this holds for any k. This gives us our contradiction. I'm seeing some confused faces. Anyone need me to clarify or go over anything again? Okay, I'll move on. Okay, that example up there in the paper in section 6, that has this order where f is the logarithmic transform of the desired little f. Okay, now that holds, but that sort of means that the order is 12. We'd like to bring that down because really 1 gives us finite order. We want to get down from 12, and we can. We mess with the tracts because we're talking about hyperbolic metrics and whatever. The closer you get to the boundary, the faster you grow. So let's squeeze the tract. Let's make it thinner in parts. And the way that this is done, this is the estimate that we make use of. So the Euclidean distance from the boundary, 1 over it, that gives you this estimate on the hyperbolic metric. And so then this theorem comes about by squeezing the, if you remember in the tract, the wiggle went like that. If you squeeze the top part and make it thinner and thinner and thinner, you can then get this order of growth. And that's a bit better than 12. So that's good. Can we do any better? Because then this is just 1 plus epsilon. And we can do better. If we don't just pick thin strips, let's make them go thinner and thinner and thinner as they go along within the same one tract, you can do even better. And we end up with this result. Okay, and for those who don't know Littleo, that's what Littleo sort of means. And this is, we've gone in the space of, I think it's like 5 pages, we've gone from 12 to anything bigger than 1 to, we'd like to just get order 1 really, or like we can get as close to finite order as possible. Okay, and my project so far has been just to come up with an explicit version, because in the paper it's sort of sketched like this is how it could be done, whereas I've sort of been advised is that see if you can do the explicit construction, see if you can give the raw, gory details. And I'd have liked to have had it done by now, but c'est la vie. But that's what I'm currently working on and going forward with. Okay, and I believe, okay, so further meddling ideas, rather than just squeezing the tract to make it thinner and thinner, how about putting in these gates? that's an idea. The estimates are going to be done from there. Do the gates have to be in the middle? Do they work better at the end? These are the things I'm looking at. And I believe, so etc. That's all done. Thank you for your time. Okay. Okay.
Thanks, Andrew, for the interesting talk. Questions and comments, please. Questions from online participants?
There's one.
Okay.
So, thanks for the talk. When you say you're going to squeeze the tracts, do you mean like shrink them in this direction?
Yeah.
Like,
Ideal. Well, I don't know. We could squeeze them in another way, like bring this part out further. But
yeah, that's what I was going to ask.
based on how the constructions go, so if you go back to here where Lasse pointed out that these green lines on this one are actually in the wrong place, they should be slightly over. We sort of want the geodesic to pass through both. Whereas if we make that gap too small, based on, we want to sort of preserve the spacing. So I don't know if we can make that epsilon small, but the height
I see.
is quite all right. No, that's a good point. I'll make a note of that, actually. Thank you.
Thank you.
More questions?
It's all right.
Questions from online participants? If not, thanks to speaker again.
That's all right. Thank you, everyone. Thank you for inviting me.